you. I gotta pass back. Homework. Alright, everybody got their glasses off? I know they're nice and comfy. Just making sure. There you go. Oh, but you don't keep off. Oh, wait a second. No,
Again?
yeah, just wait. Okay, people in the front, listen now. Raise your hand with incentive. Raise your hand on why the can was crushed. Nick, I'm almost putting my glasses on. Why the can was crushed?
Number one.
The can, whichever that station was.
Like the pressure, they changed the pressure inside the can. And like
That's on the right track, but that's not the exact cause. Levi. Okay. Okay. That's not what caused it, but that's on the right track.
The expanded particles on the inside of the can had less pressure pushing on the outside of the can than the particles outside the can pushing in on the can, and there was more air pressure on the outside than there was on the inside.
So at the end, when like what you guys were saying, that they got cold again. They themselves, the gas particles on the inside of the can came back together. They halfway did implode, but the reason it imploded is because the atmospheric pressure compressed that can. Yeah.
and like water was sucked in
Water was sucked in. Why?
because of the pressure. Like it's like wind blows pressure.
Yes, but that didn't cause the actual compression of the can, but the water was sucked in due to the pressure differential. You're right. So with that though, I like that you said that, because what we did was we had a beaker of water and we had this little can with a hole in it. So what happened was the water, the air pressure drastically decreased on the inside of the can due to the fact that they cooled down. So the pressure of the atmosphere, which is in existence outside, pushed the water up into the can. Because there was low pressure here and there was high atmospheric pressure here, so the atmosphere pushed the water up. That's why there was water in there afterwards, because there was low pressure. But let me show you something else with atmospheric pressure. Good job, Clayton. So I was basically wondering what the heck caused it to compress. I know that the air particles compress on the inside, but what actually caused it to compress is the atmospheric pressure. So, atmospheric pressure. Let me see here. I have a bottle of water. Okay, maybe my demonstration. Bottle of water. It's not leaking, nothing crazy, right? I have 2 holes in this bottle. Why is it not leaking? Why is it not leaking?
It's closed.
It's closed, so what's up here?
You know. Yeah.
There is some air there, but it's actually kind of like a stable vacuum. Okay, it's not moving, right? So when I open this, where are my holes? Over here. Okay. What's it doing?
It's leaking.
Okay, why?
Yeah, now it's pushing down the water.
What's pushing on it? Air.
The atmosphere.
What? The atmosphere? It has a name.
The way you put the acid to go down to the water.
Oh, it doesn't, yeah, because it's closed off the atmosphere. So the atmosphere is being the pulling and pushing it around, and then close it, the atmosphere can't touch this. Okay. So I got one more for you. Alrighty, where's my egg? Alright, so I was boiling eggs for you guys last night. I fell asleep on the couch, and so then burned my boiled eggs, which is, I mean, that takes talent. See it? Burned my boiled eggs. But, does this fit into the blast? No. Okay. So, watch me take first. I have to ignite this cotton ball. You know me, guys. Love that fire. Burn me once.
What is that stuff?
I don't care. This is isopropyl alcohol. Isopropyl alcohol, which is flammable. Okay. I need a match lighter. Don't collapse and fall. Okay.
That was more embarrassing than I should
Here,
have.
scooch up here so everybody can see past you. That's alright, I do that like once a day. Okay, so light the match, light my cotton ball on
I
fire.
did that like 5 times. I know.
Light my, okay. Now blow yours out. Okay. So. Whoa, it was violent. It was more violent than last one. Why did that go in? Huh?
Because it's vacuum.
Well, not because there was a vacuum. What actually was the egg sucked in or was it pushed in?
Pushed.
Okay.
The pressure was lower on the beaker or the flask than the actual atmospheric pressure.
Why was the pressure lower in here?
Because of the heat.
Not because of the heat.
The fires absorbing all the oxygen.
It's so that it was a chemical reaction that reacted with the oxygen. So there's less oxygen in here, less pressure caused by the gases. So lower pressure, higher pressure, pull as a bully to push it out. How do I get it out? Light a fire underneath it. If I light a fire beneath it, it's only going to, like, it's got all the air it could ask for, right? It's not going to
Suck it out.
I'm not sucking this out. Wait. There's like alcohol in there. There is a way. Okay, so pretty much tell me what I need to do. What do I need to create up here?
Higher atmosphere.
Higher pressure. How do I create higher pressure in a closed container?
Make it colder?
Heat it. No, cooling it would actually make the gases collect together. I would heat this up. So I need to take a Bunsen burner and like cook this baby, okay? Or what you're supposed to be able to do is, I don't think I can do this right now. You're supposed to be able to blow air on the side of the egg and it blows up and it pushes it out. Somebody tried to do that one time and I did get to work, but it's like takes a lot of effort. But I have another one for you. Hold on, where's my other egg? It's right here. One more egg. They actually need me. Okay. These are extra burnt eggs. I don't know if you like burnt eggs, but I'm a fan. Okay, so I'm going to see if this works. This one I didn't wash it off very well. Oh, I got some water right here. Oops. Hold on.
Forget about that.
Gotta wash out the eggs. Okay. I gotta close my water back. I have a mess up here now. Okay. New flask. New egg. Doesn't fit. Yeah? Okay, Minnie. Does anybody have a birthday coming up? Happy birthday soon.
Mine's in about 9 months.
Yours is in March. Yours is past. You got a whole year, man. August, June. Okay. Yep, we're ready. I'm ready. All right, Benny, light my candles. Hold on. This is why you kept your goggles on. So smart.
I knew this would happen.
Okay, light my candles. I don't know. That's weird.
Sorry.
Come to me. I'm just basically trying not to light my papers on fire. Okay. So, ready?
Oh.
Hey. Did you put that on your tongue?
Yes.
Oh my gosh.
Did it hurt?
No. It's alive.
Go.
Oh, you pushed
Sorry,
it.
I had to push it because I got it stuck. I saw eggshell on it. Anyway, basically, this was supposed to go like that and push the gases that were reacting up here, cause the lower pressure system, higher pressure system. So the atmosphere is pushing it from beneath up. Sorry, I'll do that one again. My egg, that was a bad egg. So, thank you. No more matches for Benny. Nope. You're good. Thank you, my lovely assistant. Woo! Okay. So, yeah, you're good. Now we're taking notes. So we learned a lot from experience, right? Ready? She'll take notes for you. Okay. All right. So we learned a lot from experience, and you guys are going to help me explain them and how the variables are related to one another. Okay. So from the marshmallow experience, who can explain that experience? Why the marshmallow grew in size? You even sent it. Who can explain why the marshmallow grew in size? Raise your hand when you're ready. Levi. So the marshmallow has what on the inside of it?
Air.
Okay. So combine those two explanations. what did you do? Did you increase the pressure or decrease the pressure on the marshmallow? Decreased it. Add to that.
So the air on the inside of the marshmallow like expanded because the pressure was lessened on it.
Okay, so everybody right now, show me that box of air. Show me it. Decrease your pressure on your box of air. Decrease your pressure. Oh, what happened? The volume got bigger. Okay, get your pressure, get your box of air back. Increase the pressure. Okay, and volume increase. Decrease is not gone. No, can't just remember. Okay, so that's basically what is. I owe you $3. Okay, so wait a second. All right, so I'm going to go with that one first. Let's explain Boyle's law. So Boyle's law is definitely a relationship between pressure and volume. Okay, and you need to write this down. Pressure and volume, are they directly related or indirectly related? Based on our little box experiment here. Increasing the pressure does what to your volume?
Decrease.
So, indirectly or directly related? Indirectly, right. Because increasing pressure smushes your volume down. So they are indirectly related. Okay, so of all the variables we tested today, what variable did we not change in this experiment? Temperature. So no, this is assuming no change in temperature. Did you change the amount of gas inside of the marshmallow? The actual moles of gas? No, it's a closed system. Closed system means no gas should escape. So there's no change in temperature or moles of gas. Okay, so this relationship can be, being indirectly related, means that you can write an equation with it. This was on your reading guide. This should be familiar. There's a initial system, pressure 1 and volume 1, and they are equal to, the product of them are equal to pressure 2 and volume 2. That is Boyle's law. Notice we didn't put temperature in there, didn't put moles in there, because those are the only two variables that are changing. So basically, increasing the pressure here would cause a decrease in volume, indirectly related. Okay, so I'm going to go back up to the top and do Avogadro's. I did this in ABC order. So Avogadro's law deals with, I didn't do this when I ran out of dry ice. So if I had a balloon, I put dry ice in there, what would happen?
Expand.
Right, so I'm increasing the number of what in the balloon? Moles of gas. Okay, so when you expand, so you're talking about moles of gas involved, and you're talking about what? What do you mean expand? What variable is changing? Volume is changing, right? So this includes both moles of gas and volume. So this is a relationship between N is moles of gas, N is just a variable for it, and volume. And in this one, if I increase the moles of gas, what happens to the volume?
It increases.
All right, so directly or indirectly? Directly. Okay, so they're directly related. Assuming what? No change in temperature or? I am changing moles. That's involved. Pressure, right. So your four variables that we're talking about are moles, temperature, pressure, and volume. That's basically everything that can affect a gas. Okay, so this relationship is actually direct. So they actually go on top of each other in a fraction form. So first scenario, moles of the first scenario and volume of the first scenario is equal to moles of the second scenario over volume of the second scenario. So this is called Avogadro's law. So basically, most of these equations, we're going to be solving for x. Like I will tell you, oh, I had 1 mole of gas. Let's say that I had 1 mole of gas for STT. If I had that, that'd be 1 mole of gas for N1. At STT, what's the volume of that 1 mole of gas? 22.4 liters. Good. So then I said, oh, well, what if I change this and I have 2 moles of gas? I would know this one. At 2 moles of gas, we actually can automatically know what's the volume of 2 moles of gas at STP. 44.8. So you're just multiplying by 2. So this is basically, we're solving for one unknown given 3 other variables. Okay, so it's just algebra. Okay, so that's Avogadro's law, Boyle's law, Charles's law. He went to Virginia Tech. So, huh? I was going to go V&T, but yeah, this one involves V&T, volume and temperature. Yeah, so I do that so you guys remember those are the 2 variables involved. Okay, so with crush the can, yeah, I know pressure was a variable we used, but we never changed the atmospheric pressure. We don't have that kind of power, right? So we didn't change the atmospheric pressure, therefore that's not a variable that is changed. We did change the temperature, and we did change the volume of that gas. Okay, so would you say increasing temperature would increase the volume of gas or decrease the volume of gas? Increasing the temperature does what to your gas molecules? Makes them speed up, and they speed up and they expand out, actually. So they get a little more disordered. So they're getting crazier. So this is actually a direct relationship. Assuming what? No change in pressure in moles. Good. So atmospheric pressure is in moles. So how do we write the direct relationship? Was it side by side or on top? You just wrote down one. Right, they're on top of each other. So V1 over T1 is equal to V2 over T2. So basically, you need to know the variables involved in each of these laws and how they're related, directly or indirectly. And then we're going to be solving for one of these given three pieces of information. I have 2 more laws for you, though. Wait for it. Thumbs up when you're done here. Awesome. And we're going to practice some of these today, so no worries. Okay, last 2. Gay-Lussac's law. Gay-Lussac's, what variables have we not related yet? We did N and V for Avogadro's. We did P and V for Boyle's. We did V and T for Charles. And we haven't done that, you're right, but that's not what I'm looking for. So pressure and temperature. Okay, so I have this. If you put a soda can or a bottle out in the sun, you keep it closed. If you keep it closed, what's not changing?
The moles of gas.
The moles of gas, because they can't escape, and the volume of the container, because it's not open. So the only 2 things that are changing are the sun's hitting the bottle, it's heating up the gas particles. When the gas particles are inside of something and they heat up and they can't go anywhere, they can't expand, what they do is they beat the heck out of the side of the container. They collide with the side of the container so much it increases the pressure of the container. All pressure is just collisions with the inside of a container. That's it. So this is a relationship between pressure and temperature. And so if I tell you increasing temperature causes them to move faster and they're beating the sides of the container, what is that doing to pressure? Increasing as well. So directly or indirectly? Directly. Good. So they're a direct relationship, assuming what? No change in moles and volume. Good. Okay, so this one is P1 over T1 is equal to P2 over T2. So what's the only one that's different?
Oh, the Boyle's law.
Right, Boyle's law is the only one that's indirectly related. Everything else is directly related. And that's why I'd like for you to give me your box of air and show yourself that you know, like it's easy to see they're indirectly related. Now the combined gas law is a combo between Boyle's and Charles's law. So what was Boyle's law again? Pressure and volume. So that was P1V1 equals P2V2. And what was Charles's law? Charles's law was not moles.
Volume temperature.
Volume and temperature. So if I want to combine that, what am I doing with temperature within the same equation I have already started? Is temperature going to go in a numerator and a denominator? Denominator, because that's where it was in Charles's law, right? So this is how I combined it. Pretty much I had Boyle's law, and then V is already in the numerator, T is in the denominator, so I just had to divide by T. So I could circle Charles's law if I wanted to. I could go, okay, Charles's law is V over T, V over T. And then you could go, oh yeah, well, I could also circle Boyle's law. P and V, P and V. So that's how they're combined. They're just merged equations. So this is assuming what is constant? Yeah, an N in moles of gas. So that's assuming we're not taking any moles out of the system. Okay, so we have 5 rules, 5 laws, 4 variables. Let me tell you a little bit more about the variables because the variables have specific units sometimes, and then we'll do some practice problems with this. We still got like 45 minutes in class. We're doing great. Can I go forward? Good. Okay, so do not write all of this down. We explained a lot of this. The one thing that I just said to you was about pressure. This is the definition of pressure, and you need to know what causes pressure. It's all about those collisions. So we are talking about particles colliding with the sides of the container. So if there were no particles colliding with the inside of the container, there would be very, very, very little pressure on the inside of the container. And the atmospheric pressure would just crush it. So, question. What do you think cold gas or warm gas causes more pressure? Warm gas because they're moving faster, so they have more energy, is that what we're saying? They have more energy, meaning that they have more kinetic energy. So I'm actually going to scooch down real fast, and I'll come right back, about temperature. So temperature is another definition that we need to know a whole lot about, okay? Temperature is not heat. Heat is not temperature. They are not the same thing. What temperature is just a bunch of kinetic energy of all the gas molecules present in that sample, and we divide it by the number of gas particles, aka the average. So the average kinetic energy of the substance. Important definition to know. And so this is what Anna just said. She just said increasing the temperature speeds them up, which causes more collisions, which causes the increased pressure. So that's us connecting the dots between temperature and pressure. Why does increased temperature cause the increase of pressure? Basically, more collisions because they're moving faster. Okay, now temperature is the one specific unit that with gases, this is only for gas law problems, we have to convert it to Kelvin. Now I'm not asking you to add the 273.15. I'm just saying if I say, okay, room temperature 25 degrees C, at 25 degrees C, what's that converted to Kelvin? 298 Kelvin. Every single time I give you something in Celsius, and most of the time I mean like that, and I'm going to give it to you in Celsius, I want you to convert to Kelvin before you start the problem. Because if not, you'll get it wrong. The Celsius temperature and the Kelvin temperature, they're not proportional. They're not multiples of each other. So the answer, you can't like, say, I'll just divide those things. No. There's some, so they actually will mathematically work out very incorrectly. Okay, so they have to go to Kelvin there. I'm going to scroll back up to pressure. Just a second. No, a second. Yes. Here. Okay. Yeah, office. I know. We're all different. Okay, so the units of pressure we're okay with. We talked about this yesterday, right? The atmosphere is the millimeters of mercury, the kilopascals, and torr. Do you remember these? Okay, we're good with that. Volume, we pretty much know what volume is. It's just make sure that your units are either in milliliters or in liters. Okay, that's the last thing to write down. They're in the milliliters or liters. Whenever you do any gas law problems, you just have to make sure that your units are the same. For if you have two pressures, both pressures should be in the same unit. I don't care which unit, it's just the same unit. If you have two volumes given to you, make sure they're both in liters or they're both in milliliters. If not, your units won't cancel and your math will be wrong. So let's do an example. Tell me when you're ready. And then pull out your sheet, your phase diagram. Yay! Pull out your worksheet that you had from yesterday, your phase diagram on the back side. That has questions. On the back one, I'm going to do the first one with you, and then one from Charles Law with you. I'm skipping this. I'll come back to this after you guys practice some. Okay. Do you see this question? Yes. Okay. Here's the sample question. I'm going to do 2 sample questions, and then from here on out, model my sample questions. I need you guys to write down your work, because on your test and on your quizzes for something like this, I give 1 point of credit for showing your work.
Calm me down, because I was nominated to be this cheese.
Oh, put this back. Come on. That's so stupid. Okay. So, no, he wasn't. He's lying to me. Are you serious? Oh. I was like, okay. So this is a sample question where I need you to show your work, okay? Ready, Freddies? Ready? Okay. Write down the sample question with me. as you read, pull out the data. I know you guys are not always fond of word questions, so don't make it a word question. Make it a math question. Okay? So you have 700 millimeters of mercury. What is this telling you right here? What variable? What variable is this? Pressure. Thank you. P is equal to 700 millimeters of mercury. Okay. Sample of hydrogen. Okay, so it's talking about hydrogen gas. Big whoop. Has a volume. There we go. Volume. So what am I saying over here? V is equal to 500 milliliters sample. Okay, you're getting 1 point of credit for showing me your variables. That's why I'm forcing you to do this. If the pressure is decreased, so what is this? Another pressure. 538 millimeters of mercury. What will the new volume be? So question V. Now, how can I modify these P's and B's? Call them P1. Yes, okay, good. So the first information in the first sentence is P1 and V1 because that scenario was given together, so they're talking about the same scenario. So those both the ones. The second scenario given was like a decreasing pressure. What will the volume be? That goes together as well. So that's P2 and V2. So what are we solving for? V2. What law is screaming at you right now? Boyle's law. Because if you write this down like this, you will not get it wrong. There's no way you can choose the wrong law because this is the only information you got, right? So first step is givens. Second step, choose law. Third step, plug it in. Okay? Plug in. So this law is P1V1 equals P2V2. I need to isolate my variable, the one that I'm looking for. So how do I isolate it? Divide by P2 because I'm looking for this one, V2. So divide by P2, divide by P2. So what I've said now is V2 is equal to this mess. V2 is equal to P1, V1 over P2. So I'm plugging in my information and moving on. Done. But I'm going to finish up this problem with you. So V2 is equal to, what was P1? 700 millimeters of mercury. What was V1? Oh, it's over there. 500 milliliters over P2, which is 538 millimeters of mercury. What units cancel? Millimeters of mercury. Good. What units left? Milliliters. Is that a volume unit? Yes. So it's kind of a double whammy, like, yeah, right. Okay. So V2 is 651, if I remember correctly, milliliters. 3 sig figs because everything has 3 sig figs. So problem. So 651 is the answer. So the level of work that I'm expecting is show your units. Show your givens. Show me your law initially. So like right here I wrote P1, V1 because P2, V2. Show me that law. Or show me the rearranged one. You don't have to do both. I'm just showing you my thought process. So if you're good at manipulating it in your head, go for it. Because sometimes you'll have to do the cross multiplication division or the floppy dot chop. What do you guys call it? Floppy dot chop. Floppy dot chop. Got it. Okay. So whatever your method is of isolating variables. And then circle your final answer. Okay? So you guys have 4 more Boyle's laws. And then I'll do a Charles's one with you. Okay? Good. You guys have 4 more Boyle's laws on your question sheet. Focus, my children, because what you don't get done, you do at home. So if you can get all 16 done today in class, that'd be grand.